Hey smart people, Joe here. In the early 18,000s, a German physicist named Joseph von Pfeffer noticed something strange. He was looking at sunlight and as it passed through a prism and spread out on a wall, when he realized part of the rainbow was missing. All throughout the spectrum from red to violet, there were dark lines where there should have been colors. Fraunhofer couldn't explain what he didn't see, but eventually he cataloged over 600 pieces missing from the rainbow. Some were dark, some were faint. They look like a barcode, and it's a way that exactly where they are. Deciphering all these little gaps in the rainbow would reveal a hidden story that will eventually allow scientists to unlock many secrets of the universe. And this is how they did it, and how you can do it too. Bright music. The scientists who cracked Fraunhofer's code were named Gustav Kurl and Robin Bunsen. Yes, that's Bunsen. And just as you expect, they were burning stuff. Kirchhoff and Bunsen were fascinated about how different elements Yes, that's Bunsen. And as you expect, they were burning stuff. Kirchhoff and Bunsen were fascinated by how different elements glow in different colors when you put them in the flame. Like stick some table salt in there and you'll get a bright yellow flame. Try some calcium and now it's orange. Potassium is kind of pinkish. Now to study the light from these flames more precisely, they came up with an instrument called a spectroscope. The spectroscope channeled light from the flame toward a prism where it got split into all the individual wavelengths, what's known as spectrum. Then was looking another tube where they can look through and measure the result. When they looked closer, the colorful chemical flames at their spectroscope, they saw narrow bands of light at specific wavelengths, and no two elements produced the same pattern of bands. This pattern of colors seemed to be kind of or fingerprints for each element. For instance, sodium has a distinct yellow line. Lithium creates its bright red line, while strontium is red and more. And we're able to see calcium strong lines in green and red, though it shines many other weaker ones that we can't see. Then in 1859, these two scientists made the discovery that Fraunhofer's code. Kirchhoff and Bunsen knew about Fraunhofer's missing pieces of the rainbow, and one day after sprinkling some common table salt on Bunsen's burner, they realized that the spectral lines beaming from the sodium-filled flame were in the exact same spot as two Fraunhofer's missing lines. These lines have to be related, but how? By examining sunlight and sodium flame at the same time, Kirchhoff and Bunsen were able to show that the bright lines emitted by burning sodium fit like puzzle pieces, with certain dark lines missing from Fraunhofer's rainbow. They realized that elements have a special property. If you heat them, they release light at specific frequencies, but in the front of full spectrum light, they would absorb those same frequencies. He didn't know exactly why this happened, but concluded that Fraunhofer's backlines were caused by elements in the sun absorbing specific wavelengths. And together, Kirchhoff and Bunsen went on to show that many individual elements' spectral lines match those missing lines in the sun spectrum. By decoding these lines, it will be possible to identify all of the elements in the sun contains without ever taking a sample of hot nuclear ball, a gas that's 150 million kilometers away, which would be difficult, correction, impossible. Back in the mid-1800s, no one knew why particular elements gave off and absorbed these specific wavelengths. But today we know that each element's unique spectral fingerprint is directly tied to its atomic structure. Every atom has a nucleus surrounded by some number of electrons orbiting around in different energy levels. But most of the time, these electrons sit in their lowest possible energy level, which was known as the ground state, but add energy, say by heating things up, and some electrons will start jumping up to higher energy states. These higher energy states are unstable, though, so all electrons quickly start jumping back down, and each time one returns to the ground state, it releases a photon of a very specific wavelength, carrying the exact same amount of energy that took to bump the electron up in the first place. The electrons of different elements inside has unique structures of energy levels, so you can tell what element what you're looking at just as based on the colors it emits when it's heated. For example, if you heat table salt, you'll always see the same two lines in the exact same part of the spectrum, as certain electrons in sodium absorb energy and then return to their ground state, giving off light. This is called emission spectrum. On the other hand, if the sodium is in the path of the light source, electrons in the sodium atoms will absorb any wavelengths. They have the exact same amount of energy that they need in order to jump up to that higher energy level, removing those wavelengths in the spectrum and leaving a shallow stripe in their place. Though through a spectroscope, you see what's called an absorption spectrum. This spectrum of subtraction is what happens as sunlight interacts with the elements in the sun's atmosphere and in the Earth's atmosphere too. As sunlight hits all the different atoms in its path, bumping electrons up to higher energy levels, they absorb part from the spectrum, creating the missing rainbow that Fraunhofer saw. And when you see the sun shining on an ordinary day, you can't tell that electrons have been stealing bits of light. But if you take a closer look at that rainbow just right, you can see that some of it is missing. But rather than keep just talking about this, it will be easier to actually show you. To make the absorption and emission images that you've seen so far, I made this little DIY spectroscope that basically works like Bunsen and Kirchhoff did. Except mine, you can shine a digital camera into it. And made it from stuff I ordered from Amazon. They didn't have that. So here I have an opening for the light to go in, passing through this tiny little slit, which help make everything look sharper. Then, instead of prism, I'm using something called a diffracting grating, which uses tiny little grooves to split light into its all individual wavelengths. Just put a camera right here and you can see it too. And you can see it too. Okay, so I want to check out those lines in the sun. But by the way, if you can do this on your own, never ever point to your spectroscope or your eyes directly at the sun. I'm just gonna point mine at this white thing that has sunlight bouncing off it. It's very bright. There's my rainbow, and you can see there are dark lines running through it. This is what Fraunhofer saw over 200 years ago, and thanks to Kirchhoff and Bunsen, we can actually decode these lines now. So these really dark ones you see are those are hydrogen lines. The sun is mostly hydrogen, so we have a lot of absorption there, and here's sodium. The dark line is yellow. It's actually two lines really close together, but we don't have enough resolution to make out both of them. Anyway, there are a lot of lines here, and if we're able to look at through a higher grade spectroscope, we actually see hundreds and hundreds of them. They are not all different elements, most of them are from different energy levels, just in a few elements. If we're to sit and decode all these lines, we could actually figure out every single element that's in the sun. What else you're going to be looking at? Many light sources around us reveal secrets through the spectroscope. Fluorescent light bulbs appear white, but reveal specific emission lights instead of a continuous spectrum. Sodium vapor street lamps emit the characteristic sodium line, and neon signs give off the particular emission lines of this noble gas. The amazing thing about spectroscopy is that we can use this to look at stuff that's around us or across the galaxy. Well, not with our spectroscope. We need a better one. And in principle, it's true. Now that we know the different prints of elements and compounds, physics basically becomes chronology. Based on the pattern of lines, we can decode what stuff is made in all over the universe. And in some cases, code breaking uncovers some pretty mind-blowing truths. For instance, back in 1912, American astronomer Vestal Silver was studying on the spectrum of a fuzzy little spot in the sky that he called the Andromeda Nebula. It was absorption spectrum, and it has much of the same dark lines Franzover had seen in our sun spectrum. But the weird thing, they weren't quite in the right place. They were all shifted toward to the blue end of the spectrum. The only explanation Sulfur came up with was whatever he was looking at to be moving. Because they were moving towards the Earth as it radiated light, the wavelengths would bunch up and appear bluer as they actually were. It kind of a Doppler effect. Based on how much the lines were shifted, Sulfur can even tell how fast Andromeda was moving towards us, and the answer was ridiculously fast, something like 300 kilometers in a second. Now, after that, Sulfur turned his stethoscope to a bunch of other fuzzy spots in the sky. He still didn't know what they are, but there was something weird about them too. Compared to the sun, their spectral lines were all shifted to the red end of the spectrum, which seems to suggest there were a bunch of fuzzy objects in space hurtling away from the Earth. Sulfur didn't realize it at the time, but this was the first hint that the universe is expanding. Those fuzzy spots, what he was calling nebulas, were actually far galaxies. About a decade after Sulfur, Aldrin Hubble realized that the farther away a galaxy was, the faster it was moving away from us. And he concluded that the only way that makes sense was the entire universe was expanding. The key to discovery was encoded in those same missing lines Franzover spotted in the sun spectrum 100 years earlier. Today, this missing rainbow code is even helping us in our search for life beyond Earth. As exoplanets cross in front of their stars, we can look at their starlight that filters through the exoplanet's atmosphere. New dark lines will appear in the star spectrum as the planet crosses in front, and they correspond to the elements and chemical compounds in the planet's atmosphere. Some of those could hold signs of life. So, finding an unlikely balance of chemicals in the exoplanet's atmospheric spectral fingerprint could be our first clue that something's living there. The James Webb Space Telescope is already looking at a spectra of planetary atmospheres, and who knows what it may one day discover. So, by decoding bits of information missing from sunlight, we figure out the makeup of objects all over the universe, in places we never be able to visit or touch. We discovered bizarre, mind-boggling truths about the fundamental nature of our universe. We may soon be able to search for life on a planet that's light years away. All of this is thanks to some electrons swiping little bits of the rainbow. Stay curious.